In today's lectures, we are going to discuss chapter 5, which is called Shear Strength of the Soil. We have studied in we are going to study chapter 5, Shear Strength. Before that, we studied chapter 4, Total and Effective Stress. We studied chapter 3, Soil, Water and Permeability. Chapter 2, Site Investigation. And chapter 1, it was Soil Classification. To go through this lecture, this is an introduction to design foundation and to ensure safety of the soil under the influence of the structure. And we have to check the following. Calculate the stresses on soil, calculate the bearing capacity of soil, design the foundation taking a proper safety factor. To calculate the bearing capacity of the soil, then we need to understand what is the shear strength of the soil. He is speaking about the factor of safety. This is not important in our lecture. It was discussed before. If I have a load that is acting on the soil, or I have a body and I am subjecting this body to two forces, a vertical force and a horizontal force. Of course, the vertical force, once I put the vertical force may be the own weight of this element. So the own weight is there. It has a reaction coming from the bottom. It is stable. If you put something, it will be stable all the time. If you start to apply this force F, when you apply this force F, at the beginning, nothing will happen. You start to apply the force, the body is standing still. If I have this bag on the table and I start pushing it with one finger, it will stay in place, nothing will happen. Then if I push harder, maybe it would stay a little bit more. And then if I push with my palm of the hand, it will start to move. So there is a limit when I apply this force F and this body starts to move. It means what? It means that there is some kind of reaction, another force acting in the opposite direction, but this opposite force has a limiting value. Once I exert a force with more than this value of this force below, then the body starts to move. But before that, it's not moving. So there is a frictional force, we can call it a frictional force, which is the force existing between two bodies, upper body and lower body, or any two neighboring bodies. If one tries to slide on top of the other, there is some kind of force that will prevent it from sliding. To make it slide, I have to push harder. It's as if similar to something, but of course it is a little bit different because I'm going to speak about a car. If I have a car, very heavy car, and I ask somebody to push me, he will come alone, he will try to push me, the car is not going to move, because he is exerting a force that is less than the friction between the soil and the land and the car. Then maybe somebody else will come and help him, then in this case they start to move. Of course, this is a little bit different because there is tires and these tires have a rolling effect, but anyway, it is the same sense. It means that you have to exert more pressure than a limiting value to start sliding your body. Let us discuss this. If I have somebody sliding on top of ice and somebody sliding on top of grass, I think we may have discussed this before. Whoever who is sliding on top of ice will slide easier. It means that this force that is preventing the sliding of any body is affected by the type of material. Because if I'm sliding on top of ice, if a small boy come and pushes me, I will slide. But if I'm sliding on top of this land, it will be very, very difficult for me to slide. So it depends on the type of material. It also depends on the roughness of the surface. If I have this box on top of this platform, to make it slide, it may be difficult if the surface is rough than if it is sliding. This is exactly the same for this example, because for ice it is smooth, but for normal soil it is not smooth, it is rough. So in this case, the roughness of the surface defines this type of force. And also, suppose that you are using the same type of soil. This boy trying to not push, move, he's trying to move this raft on grass. But for two cases, one with load on top of it and one without load. Of course, the case without load, it is easier. So it means that if you have the same material, then the normal force will affect it. So now from these two figures, we come up to that to slide something on top of another, there is some kind of friction or resistance. Let us call it resistance for this motion. This resistance is affected by two things: by the types of materials due to the roughness of the surface, and by the vertical load acting on this surface. Let's discuss this reaction. We said that there is a force that is preventing this motion. This force is affected by two types of soil properties. Let us first discuss this force. They said that this force is equal to, which is the frictional force or the resisting force. This resisting force is equal to the vertical force multiplied by something called mu. Mu is a coefficient. So mu is the coefficient of friction between two surfaces. F friction is the maximum shearing resistance between two surfaces. This mu is equal to tan phi. Tan phi is the phi of the soil. So here I have something related to the vertical force. Fv is the vertical force or the vertical stress. Mu is something related to phi, which is something related to the type of material. So this is in case of phi material. But is this the case only? Is it only phi material that has problem? No. It also happens with material with cohesion. To understand this, we have to understand what is the difference between friction and cohesion. If you take a bucket of sand, pour it on the ground, you will find that the sand is having this pyramid shape. Why is it taking this pyramid shape? Because there is friction between particles of the sand. This friction enables particles to ride on top of each other and to make some kind of friction between each other. On the other hand, I have something called cohesion. This cohesion is related to clay. So friction was related to sand. Cohesion is related to clay. If I have a piece of clay, I can shape it like this. I can shape it like this, I can shape it any way. I cannot shape sand. If I give you some sand, you cannot shape it. But there is special property in clay that enables clay to be shaped. Particles are joined together with a special force which is called the cohesion. This cohesion is different than the force of the friction. You can now understand what is the friction. The friction is between the surface, it is the roughness of the surface. The cohesion is the bond between particles. It may be due to static charges on the material. So materials are joined together. That's why they can carry tension. I can shape any shape I need because they can carry tension. But here they cannot carry tension. They just roughness between surfaces. So in this case, this additional force, now I know what is the additional force due to friction. It is tan phi multiplied by the vertical force. The force due to cohesion is just the C of the soil multiplied by the area of the contact surface between the two layers. So I have two parts. If I have C soil and phi soil in the same time, then the force of friction or the force of resistance will be the summation of tan phi multiplied by the vertical force, this is due to phi, and C multiplied by area, which this is due to the cohesion. Just something to remind you, to understand what is the difference between cohesion and friction. This is the photo for the friction, and this is the photo for cohesion. Remember these two photos because they are easy to remember. This is pure friction and this is pure cohesion. Suppose I want to understand more what is this cohesion and what is this friction, then imagine that you are looking at a sample of soil under the microscope. Imagine that these particles, these are just beads, small beads. If these beads they resemble soil particles that has no cohesion and no friction. If I have few beads and I put them on the ground, they will spread on the ground. They will not have this pyramid shape due to friction, and they cannot be shaped. I cannot put 2 or 3 next to each other and they can pull each other together. So this is a simulation for soil particles that has no friction and no cohesion. Just imagine that these are the soil particles with no friction and no cohesion. Suppose that you want to add friction, take them, try to roughen the surface. Use any abrasive material. Try to roughen this surface very, very good. The more the surface is rough, the more that when you put these beads together with different sizes, small, big, medium, and so on, they will a little bit take this pyramid shape. So this is how you induce friction to a material with no friction. Suppose I want to induce cohesion. What should I do? I will bring any glue. Add this glue on top of the surface. What will happen? Once the glue starts to be stiff, you can make any shape of this material. So cohesion is like a glue that binds together material that has no cohesion, and friction is the roughness of the surface that try to prevent particles from sliding on top of each other. So this is, remember these three things. By remembering these three photos, remembering this, you will know exactly what is C and what is phi And what is C5 soil? If I tell you I have C5 soil, what's the problem? I have soil with rough surface and with gluing material or cementing material all around. Why not? I can have both features together in one material. Okay. Yes, to answer your question, if I take this and heat them, they will melt and they will induce cohesion. If I crush them, they will be broken into pieces with rough surface, so they will induce friction. So it's another type of imagining how we can induce friction and cohesion in soil, or how friction and cohesion really works in soil. So to conclude from what we have studied, there are two types of forces: frictional forces and cohesional forces. Both, when summed together, they give us the horizontal force that prevents the sliding. What is this horizontal force? It is FV multiplied by tan phi, this is the frictional part, and C multiplied by A, this is the cohesional part. This is the start of our equation. Divide by A, so if I divide by A, I will end up with this shape. I will end up with this equation. This is the equation, the shear strength equation that we want to reach. It says that tau, which is the shear strength, shear strength is the friction, the horizontal forces that is preventing sliding divided by the area. This is the shear strength. FV by FA, it is the normal stress. So it is the normal stress multiplied by tan phi plus C, because here A divided by A, they cancel each other. So this is the shape of the equation of the shear strength. This is what I want to reach. Here's some important notes. Soil collapses always soil collapse always occurs as a result of shear stresses. This is the normal. Soil does not collapse due to vertical force. If I take a piece of soil in my hand, I try to squeeze it, it will never be squeezed. So when I increase the normal pressure on soil, it is never, it will not collapse, but it will be stronger. It may be, it will reduce in size a little bit, but because it is reduced in size, it became stronger. So, but it will not collapse. But if I take a piece of soil and I try to squeeze, not to squeeze it, not to crush it, but to split it into two parts, in this case, it will be split very easily. So I'm actually shearing the soil. So soil usually fails by shear. It's not increasing the pressure on the soil does not do any harm, but increasing the pressure that induces shear stresses produces the problem. That's why if you are standing on soil, the soil beneath you never fails. But what happens is the soil around you fails and you may penetrate the soil itself. So it is the shear between the soil particles that induces the failure. It's clear that the soil collapses due to shear stresses like a shape of an inclined surface. I will show you a few shapes for soil that collapse, and you will find that these collapses are always due to shear. Here, part of the soil has already collapsed because of shear. Here, part of the soil has already collapsed because of shear. Maybe the other portion, it may have left the soil as one block. It may have happened like this, but two blocks are sheared away from each other, so failure occurs. Here also, this bulk was it revolved and slided away. So maybe this is one block, but it was here and it was sheared to move to this location. Also, this is another shape for part of the soil that has sheared away. This is important. Normal stresses that affect the soil causes settlement. This is what we have just said, but not failure. If I have soil and I compress it, it will settle. It will be compressed, but it will never reach failure. To reach failure, it means that part of the soil is compressed and part of the soil is not compressed, so there is a shear between the compressed part and the part that was not compressed, then I have problem. But if the full amount of soil is compressed, it will never fail. We said that we have C and phi. You remember the equation? Here is C and here is phi. These are the two major important factors that are included in the shear strength formula. To get this C and phi, I can do shear strength tests in the laboratory. One of these tests is the direct shear test that you are going to conduct in next lectures in the shear box testing. This is the equation that we have just reached. We said that the shear strength is equal to C plus sigma, which is the vertical stress, multiplied by 10 phi. This is a presentation of this formula. This is here stress, here is the shear, this is the shear and this is the normal stress. The relation between the shear and the normal stress is, if I trace this formula, it will draw this line. This line, if you substitute in this equation with a normal stress of 0, if this is 0, then in this case, what will be the value of the shear strength? It will be equal to C. It means that when the stress is 0, my point is at this location, it is C. And then it starts to increase by a value sigma 10 phi. This is phi, this is the slope of this phi angle, it's the slope of this line. And the more I increase the value of sigma, this line is traced to get this shear strength. So this is just a graphical presentation of the equation that we have just proved and found to be the equation of the shear strength. We have just said this, the definitions. What is the phi angle? It is the angle of friction between soil particles. By the way, you don't need to memorize definitions. We have just understood what is phi and what is C. But this, if you want to put it in words, this is how you can put it in words. Phi is the angle of friction between soil particles and depends on the surface roughness of the particles. C, it's the coefficient that expresses the cohesion of soil. It has a value only in the case of cohesive soil, while it is equal to 0 in case of cohesionless soil. Factors affecting shear strength. If this is my graph, from this graph, what can we deduce? What will affect the value of, let's see this, this is the equation. What affects this value? What are the parameters that affect this value? The value of phi affects, the value of C affects, the value of sigma affects. So this is just, so it is C and phi and the normal stress. This is just a translation of the equation. It means that the shear strength is affected by the normal stress and affected by the C and phi. Okay, take these and try to put them into soil properties. Type of soil affects C and phi. Water content and relative consistency affects C and phi. Void ratio and relative density also affects C and phi. Grain size and grain shape affects C and phi. It means that all of these are parameters that we have studied last year before that in previous chapters. Then these parameters can affect me in the value of C and phi, so it affects the shear strength of the soil. How can we solve a problem for shear strength? To solve any problem in geotechnical engineering, I have to expect the behavior. If I can expect the behavior, then I can solve this problem, because I can never simulate the soil problem 100%. I always have to make some approximation. So to make these approximations, I have to understand the behavior a little bit. If I have a footing here, and this footing, I have a load on top of it, what will happen to this footing? This footing will push the ground below. So I can divide the soil into few zones. Each zone has a specific behavior. The triangle below this zone is triangle that is completely compressed by the soil, by the footing. So this triangle will move down. Then I have a wedge here, number 2, and a similar wedge in the other side, number 2. It's going all around the footing. So this wedge, when the triangle number 1 pushes below, it pushes wedge number 2 to the sides. So the wedge number 1 goes down, wedge number 2 goes to the side, wedge number 3 is pushed up. So what happens is part will go down, part will move horizontally, and the part will move vertically and will push everything on top of it. This is the normal approximated behavior of soil in case of loading with a footing. If you stand with your feet on top of soil, you will find that the soil around you goes up a little bit and you go down a little bit. What is happening below? This is an approximation of what is happening below. Part following your pressure going below, part following the pressure of part number 1 and moving horizontally, and then part moving up everything on top of it. And here this is a repetition that the failure occurs in case of shear. We have 3 types of shear. We have something called general shear failure, another type called local shear failure, we have punching shear failure. General shear failure, this happens in good soil. If I have good soil, then this good soil, we will discuss it later. Just concentrate on the name. It is a general shear failure. It happens in dense soil. Here it is a local shear failure. It happens in intermediate types of soil, and we have the later punching shear failure. It happens in loose soil. You remember this drawing? We said that this is the shape of the approximated behavior of the soil. If you go here, this is called the general shear failure. So this is this case, the general shear failure. We said it happened with good soil. Why it happens with good soil? Because with good soil, it is a little bit hard, So it can act as blocks. If I have stress here, it can be transferred from this point to this point, and then from this point to this point, and then from this point to this point, and so on. To push something, and this something pushing something after it, it means that I'm pushing strong material. But if I am pushing soft materials, once I push them, they will be compressed and nothing will be transferred to the other side. So this is the case in case of dense soil. The next type, which is the local shear failure, this is an approximation for it. The soil is intermediate. So once I push this part, the load will be transferred to the next wedge, but it will not go further beyond this. So it will be local shear failure because it sheared the area around it. The third type is the punching shear failure. This is the third type. It is called the punching shear failure, where the soil is very soft to the extent that once I push the soil, the area below it is compressed, and that's all. It cannot move or transfer the stress to another area after it. So it is just punched in place. It shears the place where it exists and does not go anywhere beyond it. What are the applications of shear stress? Why do we study shear stress? Because we are going to study it in what? In stability of slopes. Of course, before that we were discussing normal footings, shearing of below normal footings. Here it is stability of slopes. If I have a slope, this slope wants to be sheared. So in case I want to design it to be safe, I have to prevent shearing forces from shearing this slope. I can also study it to design retaining structures. If I have a retaining structure or something like this, I want to have soil on two different levels, then I will make a wall to separate the high level from the low level. In this case, I am preventing shearing of the soil using this material. If I have here, imagine that this is a slope. Instead of a slope, I have a wall. The soil itself wants to be sheared like this. So if I put a wall, it will prevent this wedge from falling. So it is, I'm preventing shearing stresses. Here we are going to study something that is very important. If I have a block of soil, I'm subjecting this block of soil to few stresses. It's the stress on top and the stresses all around. It may be called, of course, the stress on top is sigma 1. The stress all around, it may be called sigma 3, or it may be called sigma 3 and sigma 2 in case I have different values for horizontal stresses in case of soil that it is not isotropic. But let's imagine that we have isotropic soils. It is only sigma 1 and sigma 3. Sigma 1 is the major principal stress, which is the stress in the vertical direction or in the major direction. The bigger stress is called sigma 1, and the smaller stress is called sigma 3. Imagine that you have a sample like this, any sample. Imagine that you're having this mobile and you start pressurizing this mobile from the top. How would you expect this? Imagine that this is a block of sand or block of clay. How will this block be? How will failure happen? If you think of it and try to imagine, if you are exerting this pressure, and you have pressure all around with a smaller value, you will find later when this sigma 1 increases that my sample will be sheared like this. Part of the sample will slide on the other. So I will have an inclined plane for this failure. It means that though I am exerting stresses sigma 1 and exerting stresses sigma 3, the soil failed on another plane. It did not fail on the plane of sigma 1, and it did not fail in the plane of sigma 3. It failed on another plane having, suppose that I am exerting sigma 1, AB should have been the plane of failure, but it is not the case. If I am exerting sigma 3, BC should be the plane of failure, but it is not the case. I have another plane called EF, and this is the plane of failure. It means that the plane of failure is the result of sigma 1 and sigma 3 on an inclined plane, and in this case it will have two types of stresses, not sigma 1 and sigma 3. It will have something called sigma and tau, vertical stress and horizontal stress. So this is the plane of failure. It is inclined with an angle phi, and these are the stresses acting on the plane of failure. To get out of all of these definitions, then in soil, if I have vertical stress and horizontal stress, both will result in a major stress or a critical surface that is inclined with an angle phi, and it will fail on this surface. This surface will be subjected to something called sigma and something called tau. This sigma and tau are the normal and the vertical and the horizontal stress, and these are the stresses that caused failure in the sample. It is not sigma 1 and it is not sigma 3. These are internal stresses that were generated because of sigma 1 and sigma 3. This is the relation between them. If I want to calculate the normal stresses, it is sigma 1 cosine phi and it is sigma 3 sine phi. Just تحليل للforces, just resolving the forces into this other direction. So this is the normal stress and this is the shear stress, the relation between them and sigma 1 and sigma 3 that was applied on the sample. Now somebody that is very clever, something like, you remember Newmark chart that we have studied before when we are studying stresses. Now we have somebody else called Moore. This Moore presented a circle, it's called Moore circle. Moore circle relates everything together in a graphical way. This is Moore circle. This is sigma 1. This value here is called sigma 1. This value here is sigma 3. And he drew a circle between sigma 1 and sigma 3. And this circle represents the normal and shear stresses on any inclined surface. If I want to have, say in this drawing, I want here the stress at phi. Suppose I want to make another angle, it is equal to 2 phi. I will go to this point, take an angle equal to 2 phi. It will cross this circle in a point. Take this point, go down and go horizontally, it will give you the normal and shear stresses. So this very clever presentation made me able to get the value of the normal and shear stresses at any inclined surface. So drawing this and then taking any inclined surface, will give me the exact value of normal and shear stresses at this location. These are some, what are the major principal stresses and minor principal stresses, sigma 1 and sigma 3. We discussed this on the drawing. This is major principal stresses. They are the stresses affecting the major principal plane and are the largest vertical stresses affecting the plane in a sample, and the shear stresses are equal to 0. Anyway, these are just definitions, just read them. But what is important for us is this drawing. This is the Moore circle. If I need to, if I have here a sample subjected to sigma 1 and sigma 3, I go to this drawing, I put here the value of sigma 1, I put here the value of sigma 3, I consider this is the radius, the diameter of a circle, draw the circle, and using this circle, I can give you the stresses, the normal and shear stresses at any inclined surface. How? Just draw the inclined surface, measure the angle, take this angle, draw it here, cut the surface at any point, you will get the normal and shearing stresses at any point. This is, by the way, equivalent to substituting in the equation. If I take the equation of the normal stresses, then I can get it in terms of sigma 1 and sigma 3. But this is just using graphical presentation. By the way, this point is called the pole. This point pole is the point where I can draw any inclined surface. If I draw here an inclined surface with a very small angle, it is equivalent to an inclined angle here, and I can get the stresses. So, which one is the surface that will cause failure? Moore said that the surface that will cause failure is, of course, he made lots of trials till he discovered which point is this the plane of failure, or this, or this, or this. This we will see in the next slide. He said that you remember our equation that shear strength is C plus sigma 10 phi. What he did is that he drew this line and he started with the value of sigma 1 or sigma, suppose we start with sigma 3. I think it is in this next slide. Yes, this is the failure line, and this is sigma 3, which is the stress around my sample. Then I start to put sigma 1 on top of my sample. If I put a small value of sigma 1, then I have this circle. This circle is not a failure circle. Nothing will happen. Then I try to increase sigma 1, sigma 1. Every time I increase sigma 1, I draw a bigger circle till I touch the shear envelope in a point. Once I touch it in a point, this is the point of failure. So at this point of failure, if I draw a circle that is tangent to this line, then this is sigma 1 at failure. And if I want to know the normal and shear stresses at failure, then I go down here, this is the normal, I go down horizontal here, this is the shear. If I want the angle of inclination, I just connect this point to the pole and I measure the angle. It will be the angle of the shear of the point of the plane that will be sheared. You remember here we were drawing here angle at any location. If I connect this point to the pole, I can measure the angle, this angle, and this angle will be the angle of the stress here. But in my case here, I am measuring the angle at the location where I have failure. So from this drawing, I can know the angle at the location of the failure or the inclination angle of the plane of failure. This is, we have here two angles. We have phi. Phi is a soil property. Phi is the frictional angle of the soil. This is another thing. But this angle, which is theta, maybe I said it before wrong, but this is theta. So if I have this angle theta, this the angle of inclination of the plane. It may be the plane of failure or it may not be the plane of failure. How I will know which one is the plane of failure? By drawing the line, which is this line. Draw this failure envelope. When I draw this failure envelope and I have sigma 3 is the confining pressure all around. So if I draw few circles, I will increase the value of sigma 1 till I touch this. Once I touch this, then it means that this is the more circle at failure. So this is sigma 1 at failure. So this is sigma 1 that will cause shearing failure. And once I know this, I can get the shear stress at failure and the normal stress at failure, and I can connect this point to the pole here and measure the angle, and it will be the angle of inclination of the failure plane. This is my case. We said that here any circle, any dotted circle here is not the failure circle. The failure circle is the first one touching the shearing envelope. This was for a case of fixed value of sigma 3. Suppose I have the same soil, but I have different sigma 3. If I have this point, I have sigma 3. Then for this sigma 3, there is one value for sigma 1 that will initiate the failure. So from this circle, I will draw, from this point, I will draw a circle tangent to this point, and this point will be the failure surface of this sigma 3. If I have another point for sigma 3, then it will have different sigma 1, different everything, every time I draw. So it means that using this chart, this chart is for a fixed C and phi, for a special type of soil. But you can insert millions of circles depending on the stresses that you are applying on the soil, sigma 1 and sigma 3. And there is one combination of sigma 1 and sigma 3 that will induce failure to this soil. Similar to this one does not induce failure, but this one induces failure. So the same here. If I draw here a small circle, it's not failing, but if I draw the tangent, then it is failing. Here also the tangent one is the failing, and here the tangent one is the failing, and so on. So how to determine the shear strength parameter? I think we can stop at this point and continue next time. But next time we are going to discuss how, now you have seen that it is very important to have C and phi, because once I know C and phi, I can draw this line, and this line is the line that defines the failure. I can start now putting any combination of load and checking. If I tell you I have a sample with sigma 1 equal to so and so and sigma 3 equal to so and so, you are going to draw this circle. If it is below the line, you will tell me it is safe. If it is tangent to the line, you will tell me that it is the start of failure. But suppose you draw it, this is a very tricky question. If I tell you that I give you sigma 1 and sigma 3, and I find that the circle is not tangent, it is crossing the line, what does this mean? Does this have a meaning in soil? Can the circle cross the line? Actually, it will not cross the line. Why? Because once I have a fixed value for sigma 3 and I increase sigma 1, once I reach the tangent point, then the sample fails. I will not have a sample. So how come you want me to cross the line and draw a bigger circle? It's an imaginary circle. It's not a real circle. Because if I have the tangent one, then the sample is destroyed. I don't have any circles to draw after that. So this is just something that you need to think of it. But next time we said that this line is defined by C and phi. So it is very important for me to define C and phi. How can I get this C and phi? Next time we are going to discuss it. Either we can get it from lab tests similar to the triaxial, to the direct shear test, the one that you are going to do by your own hand, and there are other also field tests that we can discuss also. We can stop here and see you next lecture. Thank you.